Welcome to the Simonyi Lecture for 2013. My name's Marcus du Sautoy. I'm the Simonyi Professor for the Public Understanding of Science. And the Simonyi Lecture is, in some sense, one of the highlights of the year in Oxford for trying to promote science, tell the stories of science to the public. And it's always fantastic to have this welcome from the Playhouse to host this lecture, a great place to tell stories on the stage here. I'd also like to thank the Amalur Foundation, who funds the lecture, makes it possible. This year's lecture is Professor Ian Lipkin. Ian is the John Snow Professor for Epidemiology, Professor of Neurology and Pathology, and Director of the Center for Infection and Immunity at Columbia University. But more importantly, Discover magazine described him as the world's greatest virus hunter. I met him last year, actually, at a meeting about this time in Goa, in India. It was an amazing meeting which brought together people from so many different fields, politics, art, science, sport. It was a very exciting meeting, but Ian's lecture was the one that really stuck out for me. It was exciting, actually quite frightening as well, so I hope you don't go away having nightmares after today's lecture. But actually, slightly reassuring that there are people like Ian in the world who are helping us to fight the viruses and microbes that Ian's going to talk about. So he's going to be giving a lecture of Microbes and Men, Tales of the Small Game Hunter. Please give a great Oxford welcome to Ian Lipkin.
Thank you very much, and I'm delighted to be here in Oxford. This is my first time here in 35 years, and I can say it hasn't changed. And I think I was speaking with one of the reporters for the local newspaper, and I told her that to prepare for this lecture, I was looking at old episodes of Inspector Morse, which I love very much. I'm not as crazy about Inspector Lewis, but I guess that's just a reflection of my age. What I'm going to try to do today is walk you through actually three topics. One of them will be public media and perceptions of infectious diseases. Then I'll talk to you about pandemics, and then I'll talk with you about future perspectives and where I think this field is going. I like to start this lecture with this particular photograph, which is from a review that I wrote a few months ago, but it's a very nice picture of a small game hunter, and you can see all the trophies up on the wall in front of the fireplace. So unfortunately, in my home, you can't really see a fireplace like that. Neither can you see those, but that's my sort of imagination of what it should look like. Now, this is just a small disclaimer. I love microbes. They support me and have done so for many, many years. So although I'm talking about the bad aspects of them for most of this lecture, the fact of the matter is we need them. They are our fellow travelers. They outnumber us 10 to 1 in our guts, even more if you consider the skin. They are sprinkled throughout our genomes. They have been critical in the evolution of mammalian species, and without them, we wouldn't be talking here today. Additionally, we've begun to learn that gut bacteria in particular have the capacity to promote digestion and to tune the immune system. And as I will show you, they have bad aspects and good aspects. But there is some substance to some of the comments that you may have heard from your mothers and your grandmothers and such, that you are what you eat, because we are learning a great deal more about this, and I will get into that as we go through the talk. So again, pandemics and popular culture, pathogens and pathogenesis, and future perspectives. So let me begin by talking about pandemics and culture and infectious diseases in culture. So the notion that there are bizarre behaviors that are transmitted as a result of creatures who lurk in the night, in a full moon, for example, like a werewolf. These go back many hundreds of years, and you can see here now a figure who's consuming this child, and then the child becomes a werewolf and so forth. And then there's Dracula, which is a transmissible curse as well. And many of these sorts of themes have come to have been the grist for movies and stories that we continue to read and see today. The other thing, which is a very important vignette, is the notion that if you fly too close to the sun, if you get too close to something that belongs to the gods, you will be punished. And this theme comes across as well in many of the films that have been made into movies that deal with pandemics and such. And you can see this here with Frankenstein by Mary Shelley. So there have been a wide range of movies that have been made on topics relating to infectious disease. I like to refer to these as pseudoscience. They're quite entertaining. There's a Frankenstein lineage, which sort of harks back to Prometheus and Frankenstein. And then you have the Dracula lineage, which largely has been promoted by Richard Matheson, who died last year. And there have been a number of films that have come out following his book. My favorite is The Last Man on Earth, which Vincent Price considered one of his best movies. I don't have time to show it to you. There's Charlton Heston, The Omega Man, which is absolutely terrible. It's so bad, it's good. And then you have, both of these lineages coming together in I Am Legend, which is a real piece of crap that made an enormous amount of money. And then you have, so I'll go through some of those first by way of comparison. So we'll start with Warning Sign. This is a film that was made in the 1980s. It was inspired by a virus that I worked on at the time called Borna disease virus, and it's a lot of fun.
You ever hear of Borna?
You mean like born again?
No. It's a small town in East Germany. There were some horses there, this was before the war, that were attacking each other and everything around them until they dropped. It was worse than rabies. Well, it turns out that they had caught a hitherto unknown virus that was infecting the rage center of the brain, the rhinencephalon. The Borna virus is hard to catch. It's no good as a weapon. But what Nielsen did was to take the deadly part of the viral genome and move it into a nice, highly infectious bacterial vector.
I mean a germ.
Exactly.
Speaking technically, it's a germ.
Maybe we should put him up for the Nobel Prize.
Don't laugh. He's the best chimeric gene splicer on the planet.
Holy shit. Full symptomatic manifestation in under an hour. You want me to unzip? I am not coming out of this suit.
You already unzipped. For the photo, remember?
Yes, but I feel fine.
What are you talking about? We're already infected. Lactobacillus luminensis.
I don't get it. Where is everyone?
Maybe they got out before the alarm.
So the zombies always have to
left their
die,
helmets.
and then they come back to life.
There they are, asleep on the floor.
Tilt down. Zoom in.
Jesus. You'll be all right. Take it easy. You're gonna be okay.
So this clearly merits a Nobel Prize, don't you think? Now, I'm not going to show you the delivery section. That's a classic sort of American view. You have Sam Waterston. Some of you may remember him from a number of television series. He develops this cure, which I'm going to show you in a moment. He adapts it to a gun. So if you ever see this movie, you'll see a Colt pistol in the front, and then he's got this germ-killing delivery system in his left hand. So let's learn about how we find the cure.
No one's supposed to survive a direct attack from Nielsen's best weapon. Let's see if we can find out what makes you so special. Are you on any medication?
No. I take vitamins.
Are you allergic to anything? Cheese, yogurt, other milk products?
No allergies.
Or what about childhood diseases?
I had them all.
We'll take a look at your blood soon. The answer's in there somewhere.
No time. Johnny, you're late, aren't you?
What?
Your period. You missed.
Yes, a few weeks. What are you getting at?
Estrogen. Progesterone. Your blood is full of proteins and steroids. That's why you're immune. You're pregnant. Congratulations.
What can I say? There you go.
He's breathing. What's that?
I'll tell you what it looks like. It looks like a recipe.
Well, sure. The man has spent his life cooking up cures. That's what this is. It's a recipe for a new antitoxin.
I don't understand. What's Thorazine?
That's a heavy-duty tranquilizer. They use it on animals and in mental hospitals.
What's he need Thorazine for?
It knocks them out so the other drugs can go to work. 1.
This is how we do it.
Craig factor.
2.
Antitoxin.
Half.
Thorazine. Now what do we do?
We wait.
Isn't that terrific? Now, this one is again in the Frankenstein lineage. As you'll see here, this is the cure to cancer. Now, there's a very bizarre beginning to this particular story where Alice Krippman, who's the doctor who's discovered this cure for cancer, is trying to explain how this works. I don't understand the metaphor at all, so if anybody can explain it to me, I'd like to know.
The world of medicine has seen its share of miracle cures, from the polio vaccine to heart transplants, but all past achievements may pale in comparison to the work of Dr. Alice Krippman. Thank you so much for joining us this morning.
What's it all?
So, Dr. Krippman, give it to me in a nutshell.
Well, the premise is quite simple. Take something designed by nature and reprogram it to make it work for the body rather than against it.
You're talking about a virus?
Indeed, yes, in this case, the measles virus, which has been engineered at a genetic level to be helpful rather than harmful. And I find the best way to describe it is if you can imagine your body as a highway and you picture the virus as a very fast car being driven by a very bad man, imagine the damage that car could cause. But then if you replace that man with a cop, the picture changes, and that's essentially what we've done.
I have no idea
How
what
many
that
people
means.
have you treated so far?
Well, we've had 10,009 clinical trials in humans so far.
And how many are cancer-free?
10,009.
So you have actually cured cancer?
Yes, yes. Yes, we have.
Terrific. However, there's a side effect.
6 billion people on Earth when the infection hit. KV had a 90% kill rate. That's 5.4 billion people dead, crashed and bled out dead. Less a 1% immunity. It left 12 million healthy people like you, me, and Ethan. The other 588 million turned into your dark seekers. And then they got hungry and they killed and fed on everybody. Everybody.
We gotta go!
We have, however, cured cancer. Okay, now, there have been some more realistic films, films better done. One of them was called Outbreak, and that was released in 1995. And it's not great, but it's better. And it emphasizes the concept that the vast majority of emerging infectious diseases begin with wild animals and move into either domestic animals and from there into people or directly into people. And the other was Contagion, with which I was involved a few years ago. And I'll be highlighting some scenes from those as well before I move into talking about what's real and what's not in these particular syndromes. So let's start with Contagion. And what we have here is clear cutting in the jungle, which displaces bats, results in their coming in close contact with pigs, and then infecting people. And it's a bit dark, but you can see these bats eating bananas. They fly in proximity to a pig farm. They drop fruit out of their mouth, and they urinate, spreading virus, which the pigs then pick up. And one of these hapless pigs winds up being cooked. Shakes hands with Gwyneth Paltrow, and we're off to the races. Day one. Now, I reversed the order in the film for those of you who've seen it. Day one comes at the very end, but that's the general sort of gist. Now, we tried to portray as best we could in Contagion the way SARS emerged, and we were informed by SARS, and I helped put together the screenplay, and so you'll see what's a fairly accurate representation of what happened in Hong Kong. So here's an individual who's ill. He has a respiratory disease, but it's also begun to move into his central nervous system. He's developed encephalitis. He's become confused. He's walking through these crowded streets, elevators. He winds up infecting other people. This is very similar to what actually happened with SARS in 2003 in Hong Kong, and in Toronto, and in Beijing. Canary in the coal mine, lots of metaphors in Soderbergh's work. The wild animal market.
Hey.
And then we fast forward now to Gwyneth Paltrow, who's become ill. They have actually put Alka-Seltzer into her mouth to give you that foamy appearance.
Can you hear me? My name's Dr. Arrington. You're in the hospital.
Feeling well, and then this morning.
You had a seizure this morning, Beth. Have you had something like that before?
Does she have a history of seizures?
No.
Allergies, other medical problems?
I think she's allergic
fall
to
recently?
penicillin.
Hit her head in the shower?
No. She came back from a trip and she
What about drugs? MDMA? Ecstasy?
No, we don't do that.
Okay, let's get some help.
Beth.
Sir, you have to go.
Let's get a line in her.
Opening the skull is always a bad sign.
Well, the sulci are obliterated. Let's look at the base. Oh my God.
You want me to take a sample? Or?
Yeah, I want you to move away from the table.
Should I call someone?
Call everyone.
Now, we killed off 2 stars in the first half hour of the movie, which I think is a record, both Gwyneth Paltrow as well as Kate Winslet. Okay, so now we talk about the discovery of the virus.
It tends toward ovoid in shape.
And this is actually fairly realistic as well.
Like glycoproteins, but there's nothing morphologically pathognomonic.
We tested all of her antibodies. I didn't see much cross-reactivity. Her body had no idea what to do with it. It just kept amplifying.
Send it to Sussman in San Francisco. If he doesn't know what it is, nobody does.
Shows novel characteristics and appears to be chimeric in origin.
And there's a brief appearance by Jude Law here in just a second. Here he is.
In length and containing 6 to 10 genes, typical of a paramix.
We've sequenced the virus and determined its origin, and we've modeled the way it enters the cells of the lung and the brain. And the virus contains both bat and pig sequences. And in the bottom right, you can see the dark green is pig and the light green is bat. And here you can see the crossover event, bat, and pig, bat. And here is a model of the virus and how it attaches to its host. The blue is virus, and the gold is human, and the red is the viral attachment protein, and the green is its receptor in the human cells. These receptors are found in the cells of both the respiratory tract and the central nervous system. And the virus attaches to the cell like a key slipping into a lock. Somewhere in the world, the wrong pig met up with the wrong bat.
You ever seen anything like this before?
No. And it's still changing. It's figuring us out faster than we're figuring it out.
It doesn't have anything else to do.
So that modeling was actually done. It was the foundation for that modeling was actually done here in Oxford. We just adapted it for the screen.
It's mutated.
Which way, better or worse?
It's moved into an African HIV/AIDS population. The Durban cluster is highly divergent. We have a new R naught, Ellis. It's not 2 anymore.
Then, of course, the next phase is to find some way to develop a vaccine. And frequently, you're unsuccessful. It takes several tries. So very quickly, Jenner Feely is trying to build a vaccine. But as you'll see, it doesn't work out so well, at least initially.
I thought you said that once we could grow it, we could vaccinate against it.
We tried using dead virus combined with several adjuvants to boost immune response.
And?
No protective antibodies, a lot of dead monkeys.
Can you get to the part where there's good news?
Now we have to try a live attenuated virus.
Like with polio?
Exactly. The only danger with a live virus is the possibility that it will revert to wild type and kill the host.
When will we know about that?
I'll ask the monkeys.
Are we even close?
If we even had a viable vaccine right now, we would still have to do human trials, and that would take weeks. And then we would have to get clearance and approval, figure out manufacturing and distribution. That would take months. And then train survivors to give inoculations. More months, more deaths.
Well, Homeland Security wants to know if we could put a vaccination in the water supply, like fluoride, cure everyone all at once.
I'm going home now, Alice. It's getting late. Merry Christmas.
Okay, now the last vignette I'm going to show you is where they succeed. And you have this beautiful music. Appears, you see the live monkey there is very happy. You've got the wind blowing her hair. It's terrific. This was her breakthrough movie, actually. Now we had to reshoot the scene because initially they shot her giving herself a jab through tights. And as I was doing the soundtrack, I saw that and they said she would never do that. I said, what if she was in a real hurry? I said, no one's in that much of a hurry. So this is a $100,000 shot that we had to bring her back to shoot. And everybody seems to be quite taken with Nobel Prizes, so you'll hear that one come up again. But at least this time, it's for something worthwhile.
What are you doing?
It's okay, Dad.
No, it's not okay.
Do you remember Dr. Barry Marshall? Thought that bacteria caused ulcers, not stress. Gave himself the bug and then cured himself. You taught me about him. I'm testing my vaccine.
This is different. I don't want to get you sick. Ellie, you can't take that chance.
Oh, Dad, you're here because you stayed in your practice treating sick people after everyone else went home. You took that chance. You took that chance every day. What?
You won a Nobel Prize.
Yes, I know.
Very much.
Or an Oscar.
The Food and Drug Administration is accelerating approval of the MEV-1 vaccine currently in production at 5 secret locations in the US and Europe, saying the first doses could be available for human use within 90 days. The WHO estimates that it could take nearly a year to manufacture and distribute the necessary amount of the vaccine to stop the spread of the virus, which so far has taken over 26 million lives worldwide. But as labs work around the clock to produce the life-saving formula, the question remains, who gets it first?
Okay, so this is a copy of the script. It went through something like 10 revisions. Much of the time I was able to have some input, sometimes I didn't. It was cut from 2.5 hours down to about 1.5 hours because people started shifting around in their seats. If anybody's really interested, you can probably get copies of it on the internet. It takes a long time to make a movie. This is Steven Soderbergh and Greg Jacobs. I'm talking with them about what it is we're doing. This is an example of some of the edits. I don't want to spend a lot of time on this, but to show you the way the filming is done. So here's Steven, who actually shoots behind the camera, and you can see Fishburne walking on stage talking to Jennifer Ely, and from both perspectives. They have great parties. This is the Venice Film Festival, and they have very nice accommodations. Now, I showed you, by contrast, I Am Legend and Contagion. Contagion was made with a deliberate effort to be as realistic as we possibly could be, and you can see the production budget very different than I Am Legend, but I Am Legend had a much larger take on the first weekend. Domestically in the United States, a much better take, much better worldwide, and so forth. So bad science can pay better than good science, but there are a number of other ways in which you can think about this, and this movie has been very successful in developing curricula for teaching people about public health, the importance of supporting science. Now, how realistic are these movies? Well, if you look back in history, you can see that smallpox claimed 300 to 500 million lives. This is plague, the Black Death. HIV/AIDS, which is over 25 million and counting. SARS, which took 775. And in 1918, influenza killed 50 to 100 million people. To put that into perspective for 2013, that would be 250 million today. So this was a huge impact. And it's certainly as large as the First World War. So I'm going to shift now, and I'm going to talk with you about the factors that are important as drivers of emergence before I launch into a discussion of what's going to be coming on downstream. So there are many factors that are important in risks of pandemics. One of them is globalization of travel and trade. Another is urbanization, deforestation. Then we have political instability and ecological disasters. And unfortunately, we have a perfect storm now because all of these are in play, as I'll show you shortly. Over the past 2 decades, there have been, a plethora of new plagues that have emerged on the world stage. This is a heat map that shows you areas where we predict infectious agents are likely to emerge based upon the climate, deforestation, the number of people who live there, poverty, travel, and so forth. And you can see just some of these. We've got human monkeypox, hantaviruses, bovine spongiform encephalopathy. All the ones that are in red are the ones that have been transferred from wild animals to people, either directly or indirectly through some domestic animal. The white ones are those that are human to human or confined to animals. So you can see the vast majority of these infectious diseases about which we're concerned are what we refer to as zoonotic agents. Now, this is a New Yorker's view of the world, but it doesn't look that different from what you would have in London Heathrow. Global air travel is a major factor. Obviously, you can get from any portion of the planet to any other portion of the planet in about 14 hours now. And the number of countries with direct routes to JFK nonstop flights is 72. We have 190,000 international flights a year, 21 million international passengers. And this is just JFK. We have similar kinds of numbers in association with Newark, and I'm sure London Heathrow and Gatwick are similar as well. So what I'm saying pertains to all of these. The other factor that's very important is the centralization of food production. And it's not just located in one country. We're no longer eating on the same animal from a given location, serving, say, 50 families. Now we're talking about millions of people who may have materials that are mixed and so forth. And these products, pork, beef, and poultry, move all around the world. That's what we know about legal trade. Then we have a large wildlife trade. This is just what's consumed, but we also have an illegal pet trade. In the United States, we estimate that there are close to 100,000 kilograms of bushmeat that passes undetected through our borders. Charles de Gaulle is much larger yet. It's 273,000 kilograms. I don't know where the 3 came from. These are data from FAO. And China, we really don't know. I mean, that's a large red box. And we've recently begun looking into what's coming in through those borders by pursuing surveillance in samples that come in via JFK. And you can see these are primate heads here, digits, and so forth. And these are infected with a wide range of viruses and bacterial agents, all of which pose risk. And I'm sure there's nothing, this is not unique to this area. We have a huge problem with importation illegally of these wildlife products. This is an example of an infectious problem that almost certainly emerged as a result of contact with wildlife, SARS. This is an advertising campaign from Hong Kong in 2002. It said, "Hong Kong will take your breath away." Obviously, this was something that they pulled rapidly off because it wasn't particularly good for business. And this is me, my colleague Thomas Breeze at Chenzhou, who later became Ministry of Health from the People's Republic of China, and Rufu Yang, who is a scientist who'd been infected and recovered. This is the easiest way to get published in science. You simply return to the United States and get sick, which is what I did in this particular instance. The other thing is urbanization in megacities. So with air pollution, you have suppression of respiratory immunity. You have people coming in close contact with one another, sharing infectious agents, and you can see urbanization in Mexico City, Jakarta, Mumbai, Shanghai, and so forth. This, again, can be overlaid to create these hotspot maps, which give us some insights as to where we should be looking for the presence of new infectious agents. The other issue is deforestation. I showed you this in Contagion. This was the inspiration for this, and this results in displacement of wildlife, like this poor little koala sitting all lonely away from the eucalyptus trees, and even more prominent now in the Amazon. And similar things could pertain in Central Africa. Now, one of the questions that's frequently posed is, how big a threat are all these emerging infectious agents? How many of them are yet to be discovered? And what I like to tell the students is that this is a growth industry. There's no shortage of new viruses to be discovered. Our estimates are, based on some work that we did in Bangladesh, that there are at least 320,000 new viruses yet to be discovered. How many of those will cause disease in humans, we don't yet know, but it's a vast number, and it's really extraordinary to consider the possibility that there is that much uncharted territory. Now, the other thing that we need to consider in thinking about the spread of infectious agents is how humans contribute to it directly. So this is an example of an unfortunate happenstance. During the earthquake in Haiti in 2010, there was a cholera outbreak. There was poor sanitation. But the question was, where did that cholera originate? And when forensic studies were done of the cholera bacillus itself, we learned that it was identical to a strain that was circulating in Asia. And it was ultimately tracked back to Nepalese troops who'd come in under the auspices of the UN to try to help restore order. But they weren't screened at the time, and unfortunately, once it was introduced, it's now endemic in Haiti. So we have to be careful even when we want to do good. Polio. Polio, after smallpox, was slated to be the next infectious disease that was going to be eradicated. This has been with us since antiquity. This is a priest. In this hieroglyph, you can see this withered leg, which represents a polio withered leg. And you can see here the staff on which he's leaning. And Franklin Delano Roosevelt, the United States president who served while he was crippled, promoted the March of Dimes, which was supposed to develop a poliovirus vaccine. I'm fortunate. I was one of the kids who was able to get this thing during the 1950s, so I never had this problem, but many children in other parts of the world did. But this is something that we could cure, clearly. And the United Nations supported a polio eradication initiative. This is described here. And they planned to eradicate polio from the globe by the year 2000. It was an ambitious undertaking, but it was achievable. However, we didn't make it. One of the things that was, well, there are two issues recently that have come to the fore which have demonstrated the way we can get in the way of these kinds of eradication campaigns that cause problems. The first was the CIA decided to use a very clever genetic approach to locate Osama bin Laden. And what they found was by testing DNA, they were doing swabs, they were going on doing vaccines and so forth, they identified a compound in which Osama bin Laden's children and relatives were found, and they then went in and targeted him. As a result of that, the polio eradication workers, many of them were killed. It basically made for extraordinary difficulties in maintaining that polio eradication campaign. And more recently with Syria, with the loss of medical care there and vaccine protocols there, we've seen the emergence of polio again. So this is a virus that we could have eradicated, should have eradicated, must eradicate, but obviously things can go wrong, and sometimes it's humans themselves who put us at risk. Now, the most recent outbreak about which everyone is concerned is MERS, the Middle East Respiratory Syndrome. At present, it's claimed, it may be a little higher now, I've been traveling, but 144 people have died. The majority of those have been located in Saudi Arabia. And I thought I would try to give you a feel for our experiences working in Saudi Arabia so you can see what it's like to work in the context of an epidemic. So I like to call this Arabian Nights. This was some work that I did with EcoHealth Alliance and the Ministry of Health of Saudi Arabia. The first case was in June of 2012. A man about 60 years of age who we were told was in excellent state of health. And I said, how do we know he was in excellent state of health? So I was told he was going on to his fourth wife. And that's evidence that he's a virile fellow. So as usual, you get a call in the middle of the night, which is essentially what happened here. I was contacted. I then wrote a letter expressing our support and our interest in participating as a collaborating center of the World Health Organization. We then flew to Saudi Arabia. Here's a dromedary to orient you to the fact that that's where we are. We landed in Riyadh. From there, we went to Bisha, which is another airline flight away from Riyadh. Here you can see the compound. This is the house that was being built for the fourth wife. This is the favorite son. Here are two Nigerian veterinarians who are working with us, and Jonathan Epstein. So this particular first group comprised 2 Jews, 1 homosexual from the United States. We just didn't fill in those blanks on our visas. This is me sitting with the first victim's son. This is a guy who appears in every picture. We have absolutely no idea who he is. But he's immortalized. And so what we did is we went in, we interviewed people and so forth. And because we had some sequence data from the cases that had died, we immediately began looking for a bat source. And we were told that there were no bats in Saudi Arabia. So I said, well, we'll see about that. So we started looking around. We found a number of sites where we could find such bats. And here you can see a close-up of such a bat. I don't know if it projects very well, but you can see here guano, and it's dripping down from the rafters and so forth. And then plenty of bats flying around behind this man's house. They're coming within 2 meters of the ground. And this is quite eerie because the muezzin's singing, the sun is going down, the bats are flying around, and the homosexual and the 2 Jews are collecting bats. So And this is the way we do it. We have these traps with monofilament lines. The bats fly into them. They flutter down. We capture them and such. We also have these nets that we place over the cage. We measure the size of the bats. We take samples from them orally, rectally, venous, and it's catch and release, just like trout, because the EcoHealth Alliance is very concerned to make sure that no bats are harmed during the making of this movie. So, and we were able to identify in a Tophosis bat, you can see this bat here, very nice little creature. We found a sequence that was virtually identical over a short stretch to what had come out of the humans. Now, that doesn't necessarily mean that the bats directly infected the people. They could have done through some intermediate animal, and there's some people who now favor the possibility that it may be coming from dromedaries. And we can talk more about dromedaries at the end, and as you can see, people love their dromedaries. And here's us with our driver, and we're swabbing these dromedaries, and here's a very stylish veterinarian collecting samples from these dromedaries and so forth. So in the last portion of my talk, having shown you sort of the way we do this kind of work, I'd like to discuss for you where I think this field is going to go. And this may be actually the most exciting portion of this, although everybody loves the movies. But with the caveat that I have absolutely no idea what I'm talking about. Because what I'm doing is I'm speculating, except about a few things. We know that sequencing, DNA sequencing, is going to get faster and cheaper. And there are a whole series of instruments now available that are getting smaller and smaller. In Oxford, there's a company called Nanopore, which is now making what may be the smallest, most compelling DNA sequencer. Quite extraordinary. I'm hoping to learn more about it while I'm here. But the cost is dropping. So initially, when we began doing this work in the 2000s, the cost of sequencing a human genome would have been $100 million. It's now down below $10,000, and in fact, I have reason to believe it's going to be under $1,000 within the next couple of years. So we're going to be able to do far more than we could ever do before. When I began my work in trying to look at the role of infectious agents in disease, the technologies, the platforms were quite primitive. So this is in the late 1980s. The work that was required to identify a single virus took me 5 years. Now, we can do that same work in a matter of a few days. So there are literally hundreds of viruses that have been identified by us and others, and the number is going to continue to accelerate. The tools that we use for diagnosis are going to be becoming increasingly portable and inexpensive to use. This is from Star Trek, and one of the things I learned from working with the entertainment industry is that they know what things should look like. So Wah Ming-Chang, who was a prop designer for Star Trek, developed the first flip phone, which was ultimately adopted by Motorola. And if you see the most recent Star Trek movie, you can see the emblem still continues onto what they use. But this was sort of the universal diagnostic machine. And there are engineers like Ken Shepard who are now building such tools that will allow you to take a blood sample, a saliva sample, and to, at the bedside, in the clinic, figure out why someone is ill. Now, I'm going to give you an example from the first time that we use this sort of an approach to characterize a novel infectious agent. This was shortly after we became a collaborating center for the World Health Organization, where we were asked to evaluate a woman who had been tested for a wide range of infectious diseases and had not come up with any, they'd not come up with any sort of a solution. She was a travel agent who had been off on safari. She returned home. She was living in Zambia, Lusaka, Zambia at the time. She became quite ill. She was airlifted from Zambia to Johannesburg, South Africa. En route, she infected the paramedic in the plane. The nurse who took care of her at the other end, the person who cleaned the room. All 4 of these people died. This person alone, the nurse who took care of the people who were taking care of the woman who died, she alone survived. She was the only one who received antiviral treatment based on the work that I'm going to show you now. And to my knowledge, this is still the only example where rapid diagnosis using this sort of high throughput genetic sequencing enabled the detection of an agent in time. So what we try to do is to take a relevant sample, we sequence it, and we provide the information in a simple Excel spreadsheet so that the physician can look at the fungi, the bacteria, and the viruses. And in this instance, it was relatively straightforward. And as a result of what was identified by this analysis, which took 72 hours, which can now be done in 24 hours, we were able to make a recommendation. She received the appropriate antiviral drug, and she survived. Another challenge that we have facing us is that with the increasing use of transplantation and of immunosuppression of an elderly population, a whole range of things which make us more likely to become infectable, we're beginning to see the emergence of all sorts of new diseases. This is an example from a couple of months ago where we were looking at a 33-year-old woman who was a runner in excellent health with the exception of diabetes. She had a pancreatic transplant. Shortly after that, we had this problem with Hurricane Sandy. Hurricane Sandy was this huge hurricane that came through New York. It flooded large portions of lower Manhattan and New Jersey. Her apartment was flooded. She moved out of her apartment about 10 miles away to close proximity to a zoological park. Within a month, she developed blindness because she had retinal infarcts. She developed muscle weakness. And when we examined her, what we found were these particles sitting inside of cells. These were ultimately defined as polyomaviruses. Now, what we've been doing now is trying to find a way to balance the amount of immunosuppression she requires so that she doesn't reject her pancreas, yet at the other hand, not become completely filled with virus so that she has more of these sorts of infarcts. So we are increasingly seeing people with these kinds of illnesses, and we need to develop better drugs. We need to develop better screening tools so that we can eliminate these kinds of diseases. Now, I know you don't have rats like this in London or in Oxford, but we have a lot of them in Manhattan. This is Lower Manhattan, and this is really, as you can see, the bottom of Manhattan Island. So if you look in and around subways and housing developments and such, you find large numbers of the animals of this sort. For those of you who know something about Manhattan, this is right between City Hall and Chinatown. And we've been trapping these animals now for about a year and a half, and we have found a whole range of infectious agents. All I'm showing you here is bacteria for reasons of time, but they have all sorts of viruses that have potential to move from them into humans, right? So it's not just the animals that are far away, it's the ones that are very close to us that also need to be surveyed. Now, all the diseases that I've been talking about so far are those that are associated with acute illness: pneumonia, encephalitis, diarrhea, meningitis. I'd now like to talk with you about the more subtle manifestations of infection, because this is increasingly important. For many decades, people have been impressed by the notion that there might be a relationship between certain types of stress due to infections and mental illness. And both autism and schizophrenia have been mentioned. And I was originally brought in as a postdoctoral fellow in California in the mid-1980s to address the possibility that a certain number of viruses could be implicated, each with its own disease. And what we began to appreciate as we thought more about this was that it wasn't any specific virus or any specific bacterium. Instead, what was happening was the immune response generically to a bacterial infection or to a viral infection, if it occurred during a critical point during development, could have long-lasting repercussions that you might not even appreciate until someone got to be middle-aged or perhaps even older. And this is an example of that. So here, using a mouse model, what we've done is to track the amount of time or the amount of area that an animal may cover in 30 to 60 minutes. And this is an animal that's been exposed to something which we call a control. This is not an infectious agent whatsoever, but this has been done halfway through pregnancy of a mouse. So that's gestational day 9.5. A mouse has roughly a 20-day gestational period. If the animal sees a virus or a bacterium, instead it huddles in the corner of a cage. This is the same thing 2/3 of the way through gestation. Here's the control, looks fairly similar to this control, but this animal is hyperactive. So this is quite extraordinary. Same genetic background, same exposure, different timing, profoundly different effects. Now, this is a simplistic way of looking at the development of the central nervous system, so just bear with me. It's really very straightforward. You have stem cells which start more or less at the core, and they slowly move out until they get to the outer portion of the brain. So these are the neural stem cells in red. The green ones are intermediate cells, and the blue ones are the neurons, where much of the action takes place in the brain. And as you can see, there's this nice architecture that develops over the course of the pregnancy. What we've learned is that if you expose an animal to bacteria or to influenza virus or to something that triggers the innate immune system even without a virus or without a bacterium, there's a dramatic effect on the numbers of these cells that make it out to the outer portion of the brain where they have to find their connections. So this is a normal in red animal here, and this is an animal that's seen virus or bacterium or something that looks like one of the two. If we use an anti-inflammatory drug like aspirin and expose the animal to the virus or the bacterium or the mimic of a virus or a bacterium, there's no difference between the animal that sees the virus or the bacterium and the animal that doesn't. So the implication here is that it's extremely important to have immunizations against flu, for example, during pregnancy. And I predict that we will be able to identify people who are at risk for mental illness as a result of gestational infection. And those people will receive immunosuppressive agents. And this will actually have an impact in reducing the burden of mental illness. Again, a different way of thinking about infectious diseases, but extremely important and likely to be more important in the next few years. Now, the other thing that we've seen is that some people get bacterial infections and they have bizarre responses. There is a disorder known as Sydenham's chorea, which is due to streptococcus, that was described by John Sydenham, an English physician in the 1600s, that led people to try to see whether or not they could find similar examples in modern day. And in fact, what we found was that there were a group of children who responded to drugs that could be used to shut down the immune system or to remove antibodies, and this is one such rat. And these rats do these competitive behaviors over and over and over again. If you place them into a cage with other animals, they don't explore. This is the normal animal. This is the animal they don't explore. If you put another animal with them, they try to avoid that other animal, and if they can't avoid that animal, then they cower and submit in the corner. Now, many of you will have heard of Andrew Wakefield. He was the one who was the first proponent of this notion that the MMR vaccine caused autism. It took many, many years to shut down that particular hypothesis, but giving him his due, he managed to point us to a very interesting possibility that I'd never really considered, and that was that these children who had autism and gastrointestinal problems might have something going on that was worth pursuing. So we were unable to replicate any relationship between measles virus vaccine or any other vaccine and autism, but we did find that there were a group of children, roughly 25%, who had not only autism but severe GI problems. And when we began to examine those children, we found that they had a very interesting genetic problem that led to changes in gastrointestinal flora. Now, this is a very simple way of looking at the way sugars are processed inside the gut. So sugars come in this way. They come in as very long chains. They get broken up, and once they're broken up, they get carried from the inside of the gut into the blood, and there are these molecules called transporters that carry them this way. If you look at the children with autism, the levels of those enzymes that break down those sugars into smaller parts where they can be absorbed are dramatically reduced compared with the kids who just have GI problems. So we're looking at 3 enzymes here, and the transporters are actually down as well. So all of those enzymes, all the transporters are dramatically reduced in the kids. And this is all associated with a particular regulator chemical called CDX2, which controls the amount of this particular set of proteins that are produced. And when all that sugar flows from the small intestine down into the colon, the types of bacteria that grow differ from other children. So I don't expect you to read this, but simply to appreciate that these two histograms look different. And these represent different populations of bacteria. This may explain why some of these kids improve with antibiotics, with dietary restriction, or with probiotics. And there's increasing interest in the use of probiotics for promoting health. I'm going to give you another example of this, but here we're going to be talking about HIV and vaginal microflora. Now, 70 million people have been infected since the beginning of the HIV pandemic. At present, the largest burden is in women in sub-Saharan Africa, where in KwaZulu-Natal, up to 60% of women in the prime of their lives are infected. Because we have no vaccines, people have been trying to use various drugs. They've been using tenofovir gel, which is an antiretroviral gel. Some of the women are protected, but many of them are not. And the question was, what was different about those women? We found that they had evidence of inflammation. So when we measured chemicals as markers of inflammation in vaginal fluid, the women who became infected frequently had evidence of inflammation. So the hypothesis we put forward was that the inflammation was due to different bacteria, fungi, or viruses that were present inside the vagina of these women. And if we could identify that, and if we could come up with some sort of another approach, we might be able to develop vaccines that would indirectly interfere with HIV. And the answer is that at least in a pilot study, this is looking very, very promising. Again, I don't want you to focus very much on the details. Simply recognize that the colors here in the cases, the people with high levels of inflammation who wind up becoming infected with HIV is very different than the women who have low levels of inflammation and don't become infected with HIV. So this is one of the most promising things at present for addressing the challenge of heterosexual transmission of HIV. And the various bacteria that we've identified appear to be related to inducing inflammation, to having some sort of an impact on the rate at which the HIV virus replicates. Very, very important stuff. And increasingly, we're going to find interactions between bacteria and viruses that are going to be important. The last piece of very exciting unpublished data that I'm going to show you has to do with colon cancers. We're finding now that there are very aggressive colon cancers and less aggressive colon cancers. And the very aggressive colon cancers have different microflora. And we've learned that the microflora that are associated with the very aggressive types of colon cancer do not make a chemical that prevents rapid metastasis and neoplasia and all the other things that are associated with aggressive behavior in cancers. So by adjusting our microbiome, by changing what we eat, by changing through probiotics and antibiotics, the flora that comprise, as I say, the a large portion of our bodies, we may be actually able to have an impact on autism, cancer, a wide range of things, which are really going to be quite extraordinary. Okay, so I've given you a rapid tour through Hollywood, the basis for pandemics, the future of microbiological research. So I'm going to anticipate the film questions very, very quickly. So the first question people always ask, what is it like to work on a movie? And I'd say it's terrific. Are Gwyneth Paltrow, Marion Cotillard, Jennifer Ely really that beautiful? Yes, they are. How smart are they? They're all extraordinarily bright. This is one thing that surprised me. I know that, that Matt Damon had gone to Harvard and dropped out after 2 years, but these are really very bright people. Are they approachable? Yes, they are, but unfortunately not by most people. You have to somehow be involved with their receiving their paycheck. But once you get to know them, they're very, very happy. Did you have a cameo? Yes, I actually have 2 cameos, and they're a lot of fun. One of them is I'm standing behind Dimitri Martin, where the virus is first portrayed. The other is that I'm supposed to be played by Elliot Gould. Initially, they told me I was going to be played by Matt Damon. I was somewhat disappointed when they made it Elliot Gould, but so be it. And his character was based on me. How can I become a consultant? I have absolutely no idea. Did they pay you? Yes, but not enough. Is Steven Soderbergh really retiring from filmmaking? Yes, now he's making television shows because he thinks that that medium is much more interesting. Would I do it again? Absolutely. And we're trying to make a television show right now that'll be informative and will sort of take us to the next level. And lastly, the most important advice I can give you from a famous baseball philosopher named Yogi Berra: how do you do what you do? How do you make decisions about what's important, what's not? When you come to a fork in the road, take it. Thank you very much.
Well, thank you, Ian, for an amazing lecture. I think it really shows that actually, it's so important to have this communication of science, that we are informed to make decisions on things that are going to affect us all.